Hi, I just wanted to show my face. We're going to be going through some probability problems using Venn diagrams. We're going to be focusing on the union. I've been seeing a lot of you guys having a hard time with the union, so I'm going to spend a little time on that. Please feel free to contact me with any questions, comments, concerns. I have a virtual check-in for seniors from 10 to 10:30 every day. The link is attached to the bottom of the assignment. Please come and hang out. I've seen a couple of you guys in there. Shout out to Javon, shout out to Salim, shout out to Zamir. Who else has come and hung out with me? Shout out to Miles. Shout out to all of you guys that have been coming to hang out with me and just coming to say hello. We've been going over work. We went over a couple of exit ticket problems together. If you ever have like a problem, a question, it's the easiest way to like get automatic feedback from me. Other teachers come in to hang out. Yeah, come say hi. It was good to see you guys. I just wanted to show my face. We're gonna get into the PowerPoint. I'll talk to you guys soon. Bye. Meow. Sorry, that was my cat. So what we're gonna be doing is talking about how we can better use our Venn diagrams to help us understand what we're actually looking at. So just in layman's terms, a Venn diagram is usually represented by the rectangle. That's the universe. That's what we call the universe. It's like the world that the Venn diagram lives in. The events within the sample space are represented by the circles within the rectangle. So, for example, A within the universe is a Venn diagram. If I have sets A and B, there could be two circles inside of the rectangle, etc. Right. So here's a double circle rectangle inside, or a double circle Venn diagram inside of the rectangle. So with the Venn diagram, we can display visual relationships. So if we have overlapping circles or partially overlapping circles, that is indicated that this is an intersection. So this middle part here is the intersection of A and B, and that's that upside down U. Okay, that represents and. So that's saying event A and B. So if I was going to, for example, if I was going to shop for a pair of sneakers and I wanted a pair of sneakers that had red and black in it together, I would have them in the middle here because it would have both. Where B could be all of my black sneakers. So for example, I have black and yellow sneakers here, black and orange sneakers here, black and green sneakers here, all black sneakers here. But the black and red ones are in this middle circle. And then A is all of my sneakers that are all red. So I have, or all red, red and yellow, red and green, red and brown, red and orange, whatever you want, except the red and the black, because that belongs in the middle here. Okay, but then both circles together represent the union. So it's this or that. So red or black. So that could have red and yellow, red and orange, black and orange, black and black, black and red, red on red, right? So all of those things are indicative of being in either of those circles. So we represent that as or, this or that. Okay, so it's big, big, big key to remember that the union is the or and the intersection is the and. Okay, so it's really complicated sometimes when we deal with relationships. So some things could be mutually exclusive. So when I say something is mutually exclusive, in layman's terms, I'm saying that those events are independent. They have no elements in common. And if you see two circles that are not touching each other at all, that should tell you, it should be like a light bulb going off in your head, that those two events have nothing to do with each other. They don't have any outcomes that are the same. So for example, we could talk about flipping a coin and rolling a dice. Flipping a coin has outcomes head and tails, and then rolling a dice has outcomes 1, 2, 3, 4, 5, 6. If you're rolling a standard six-sided dice, those don't have any outcomes that are the same. So they have no reason why these circles, if I was to represent them as circles, that they would overlap with each other. Okay, so that's the reason why those mutually exclusive, or also known as independent events, when we represent them as Venn diagrams, those circles do not touch, right? So we're going to just go through an example of a union problem really quick. So I have a union of two events is represented by this U sign. It's the event containing all elements that belong to A, B, or both. So it's the ones in the middle too, because if I'm in the middle, that means I'm in A. It also means that I'm in B as well. So that means that I'm in the union. So for example, if I have circle A is band members and circle B is club members. So if I wanted to find the probability of A union B in the school, what I would be doing is finding the total number of students in the school. How would I do that? I would have to add up the amount of students that are in the outside universe, okay? And then I would also have to add up all of the other students, okay? I would have to add up all the other students. So I would add up 160, 35, 530, and I would add all this up, and I would end up getting 1,200. I'll get 1,200, 1,200. Now, if I wanted to find the probability of A union B, I would need to divide that number, the A union B, by the total number of students in the school. So what I would have to do is I would have to take 160, 35, 530, add that together, and I will get 725. I will get 725, and I would divide that by the 1,200, and that would give me my probability. That would give me my probability there. Okay. Now my next one, I have the intersection of two events. I have A intersection B, which is all the events that they have in common, or all of the outcomes that they have in common. So for example, we have a survey of office workers here. I have is set A, which is people who drink coffee, and set B is people who drink soda. I want to find the probability of a person that drinks both. This could be important, and let's say that you are a office manager and you need to order food or drinks for a party that you're offering for a friend, or a baby shower of sorts, or something like that, right? To find that probability, I would have to find all of the events in the intersection first, and the total number of workers in the office as well, because the total number of workers in the office is going to be my denominator, okay? And I add up all of my office workers, and I get 151. I get 151. And now what I'm doing is I'm trying to figure out the probability of people who drink both coffee and soda. So that's the middle. That's this 12 number. So I take 12 and I divide it by 151. And then that would give me a decimal, which I can turn into a percentage for probability. Okay. Awesome. Now, we're going to talk about a visual complement, because I feel like this is something I haven't shown you guys. So a complement is all the subset of all of the events that are not in the event. Okay. So for example, I have A prime or AC. So these are female high school students. So for example, set A is plays volleyball and set B is plays softball. Find the probability that the person will not play volleyball. So in set A is plays volleyball. So I have 22 and 4. I have 22 and 4. So that makes 26. So that would be someone who plays volleyball. Is that what I'm interested in? No, I'm not interested in that. I'm interested in not playing volleyball. Now, there's two options that you can go through, right? You can find the total and then take away that 26 girls that play volleyball, or you can add up 395 and 33, because you can see that those are the two numbers that are outside of the circle of volleyball, right? So I have 428. That's the number of people who do not play volleyball. But that's not a probability, that's just a number. I have 428 girls that don't play volleyball. Out of how many total girls in the school? There's 454. So what I'm going to do is I'm going to take 428 and I'm going to divide that by 454. And that's going to give me a decimal that will translate into my probability by multiplying by 100. Remember, you guys all know how to change a decimal into a percentage. Okay. Yeah. So I have a little bit more. Okay. So I have the additive rule of probability. We're going to go through that. So given the events A and B, the probability of a union of sets A and B is the sum of the probability of events A and B minus the probability of the events in the intersection. Okay, now, I know that this sounds a little funny because we're minusing the probability of the intersection. The reason why we have to do that is because the probability of A includes that intersection. Do y'all see that? Right? See, if I did the probability of A, the event A has that intersection in it already. And the event B also has that intersection already in there. So the big issue here is that I'm counting that intersection not once, but twice. And we can't do that. So that's the reason why we have to get rid of that intersection count once. Okay. So if I wanted to find A union B of this school, okay, I would have to take this probability 160 plus 160 plus 35 plus 35 plus 530 minus that 35. But do y'all see that? How, because if I'm doing the probability of A, that includes that 35, and then I do the probability of B, that also includes that 35, how I'm counting the 35 twice? Is the 35 twice inside of the diagram? No, it's not. So we can't do that. Okay, so you just have to be careful about that. Okay, so this is just an algebraic example. So I have the probability of A union B is P A of B plus P A of B, or P of A plus P of B minus P A intersection B. So here's some information. I have the probability that student belongs to a club is P of C, which is 0.4, 40%. And then the probability a student works part-time is probability of PT part-time, which is 0.5, which is 50%. The probability that a student belongs to a club and works part-time is 0.05. Okay, what is the probability that a student belongs to a club or works part-time? So the big idea here is this is my equation and I plug everything in. It's just about plugging and chugging at this point, right? So I have 0.4, which is a probability belongs to a club, which is PC. Then the probability belongs to a part-time or works part-time is 0.05. So I put both of those in, and then I subtract that one extra intersection that's included in both PC and PP of PT. Okay, that's the big understanding here, is that this is included 2 times and we can't include it twice. So we have to eliminate it once. Okay, last question. This is probability of owning a car or a pet. Okay, it is an 87% chance that you would own a car. It is a 57% chance that you own a pet. And it is a 53% chance that you own both. So what is the probability that a student owns a car or has a pet? Let's put this on let's write this out. So I'm looking for P of A, which is a car, okay, which is 0.87, okay? Now I'm going to add that to the probability of a pet, which is B. Sorry about my janky writing. So I'm adding 0.57. Ooh, I don't know why that went up there. Ooh. Okay, now once I put that together, let's think about that. What happens when I put 0.87 plus 0.57 together? I get 1.44. That's over 100%. We can't have that, right? So that's the big idea here, is when you sometimes do that, when you sometimes don't take out this extra piece, you'll get an answer that like literally won't make sense. Now I have to minus 0.53 because 53% of these people have both, okay? And that 0.53 is included inside here and here, okay? We know that that's in there, okay? And then once I do all that, I take out 0.53 and then I get 0.91. 0.91, which is 91%. Okay? All right. Thank you guys so much for tuning in. I hope you guys are safe. I hope to see you at my check-in. Please comment, email, talk to me with any issues and concerns. All right. Thanks, guys. Bye.